Yeah, thank you very much for having me, organizers. This talk is going to be about some interaction between toric topology and commutative algebra, specifically the problem of determining the homotopy type or understanding something about the homotopy type of moment angle complexes in terms of some homological algebra surrounding Stanley-Reisner rings. And this is all joint work with Ben Briggs at the University of Copenhagen. Okay, here's the obligatory slide of definitions you already know, but just to fix some notation throughout the talk, K will be a simplicial complex on M vertices, and I'll write the Stanley-Reisner ring like this. S is just a polynomial ring on as many variables as you have vertices, put them in degree 2, and you quotient that by the Stanley-Reisner ideal, so that's just this monomial ideal generated by the non-faces of K. So that's like the main algebraic object associated to K, and then the spaces will be the moment angle complex, that's this polyhedral product for the pair D2S1, and the Davis-Januszkiewicz space, same thing for the pair CP infinity, comma, a point. And then we have this homotopy fibration relating the two. And really this space has an M torus action on it by rotating the disks coordinate-wise, and that action is what's relating these two spaces here. This fibration is really like a polyhedral product model for the Borel fibration of that action. Okay, so the problem I want to talk about is just, the dream would maybe be to read off the homotopy type of a moment angle complex straight from the combinatorics of K, if you could. There are some examples where you can do that, and I'll mention them later. But in general, this seems to be a very hard problem. There aren't so many simplicial complexes for which the homotopy type of ZK is really known. An equivalent way of thinking of this, since the simplicial complex and its Stanley-Reisner ring determine one another, is just to try to understand the homotopy type of ZK from algebraic properties of this ring, right? The combinatorics of K is encoded in the algebra of the Stanley-Reisner ring. And then what is, again, an equivalent problem, but I sort of think of as a possibly easier problem, is to try to understand the homotopy type from the minimal free resolution of the Stanley-Reisner ring. So again, the Stanley-Reisner ring and its minimal free resolution determine one another. They're literally isomorphic in the derived category of S modules, so in that sense, these are equivalent questions. But the minimal free resolution is, of course, just more to look at than a simplicial complex. And I think commutative algebraists are used to this idea that if you have like a small monomial ring, half a dozen variables, and a few generators or something, the Betti numbers just get very big very quickly, and the minimal free resolution can be very complicated. So you maybe shouldn't hope to just stare at the simplicial complex or its Stanley-Reisner ring and try to figure things out that way. But instead, the minimal free resolution sort of spreads that information out in a very organized way. So you can look at properties of this resolution and see what it says about the attaching maps, say, building up ZK as a CW complex. So this minimal free resolution, all these Fs are just free S modules. I'm thinking of a minimal free resolution as an S module, where S is our polynomial ring. And basically all the invariants of a ring that you study in commutative algebra are encoded in this resolution, like this number P here, the length of the resolution is the projective dimension. Hilbert's syzygy theorem tells us that's less than or equal to M, the number of variables, but beyond that, it's sort of a mysterious invariant. The Betti numbers are there, they're just the ranks of these free modules. And so the first thing I want to do is just give some sort of interpretation of this minimal free resolution in terms of the topology of ZK. And right away we see this Tor showing up here, which hints that at least the modules can be interpreted in terms of the moment angle complex, because we have this familiar theorem saying that the cohomology, the moment angle complex, is the Tor algebra, or this Cazul homology of the Stanley-Reisner ring. And then here's Hochster's formula describing this Tor algebra, direct sum of the homology groups of full subcomplexes. But you can think of this as giving a sort of toric topological interpretation of just the modules showing up in this free resolution, right? Each F here It's just the free S module whose size is like this vector space Tor I. And also here I wanted to mention, related to this topological interpretation, something that fits nicely in this picture. Classical result in commutative algebra of Avramov and Golod says that this Kazul homology is a Poincare duality algebra precisely when K is Gorenstein. And this has a nice topological explanation, if you like, by this result of Lee Tsai, which says that Zk is actually a manifold, closed, orientable, exactly when K is Gorenstein. So that'll come up a bit later. But the natural question is, what about the rest of the resolution? Aside from modules, which are completely determined by the cohomology of Zk, the rest of the information of the Stanley-Rice ring is encoded in these differentials. So can you interpret them in similar topological terms? And the answer is yes, if you remember that the moment-angle complex isn't just a space, but it's a space that comes with a torus action, the standard M torus action. So to get at that information, we're going to bring in the group action. This torus action gives the cohomology of Zk the structure of a module over an exterior algebra. So the exterior algebra is the cohomology of the torus. So the way I think of this in like a coordinate-wise way is as follows: let lambda be this exterior algebra generators of degree -1. And then for each j between 1 and m, you can just look at the action of the jth like coordinate circle in your torus and look at what that does in cohomology, right? The contravariant map here is going to have to send any cohomology class to just one tensor itself plus, the generator, the cohomology of S1, tensor something of 1 degree less than alpha. So call that thing iota j of alpha. That determines a derivation of degree -1, because these are all coming from cohomology of this torus. They all anti-commute. So they give you a graded lambda module structure. I mean, you can do this at the cochain level, and it's giving you a DG lambda module structure there, and then that's inducing this. And this previous theorem gave you sort of two ways of understanding the cohomology of a moment-angle complex. So how can you understand this extra structure? So first of all, the algebraic way, the Tor algebra way of computing cohomology of a moment-angle complex is usually computed using the Kazul complex, or I've written here this reduced Kazul complex that came up a lot last week. So just define a lambda module structure there by letting your jth generator act by like this derivation, just like interior multiplication or differentiation with respect to the variable ui. So it's 0 on all the generators except uj. 1, and then extend that by the graded Leibniz rule, and you get a graded derivation on the whole Kazul complex. And then it's easy to see that this isomorphism that you have at the level of DG algebras is also an isomorphism of DG lambda modules. So you can compute this structure easily in the usual way you compute the cohomology of a moment-angle complex. And then the more combinatorial interpretation, that Hochster isomorphism, it's easy to see what's going on there too. These horizontal isomorphisms are those Hochster isomorphisms. So each generator of the exterior algebra, this derivation of degree -1 over here, is just looking like the map or the sum of maps induced by inclusions like this, where you add in one more vertex to a full subcomplex, namely the jth vertex. So yeah, those are all inducing a bunch of maps of degree 0, of course. So there's a shift in degrees here, but really, the right nth cohomology group here is landing in the right nth cohomology group in this big sum. Okay, so here I was going to maybe, for now, just give the example that kept coming up last week, where K is just 3 vertices with 1 edge. So if you think of the Kazul complex, or what I guess I just called it. You tell me if you can see, it's all right, but. Okay, so I guess the reduced Kazul complex here is looking like, here's our polynomial ring on 3 variables. My only missing faces are 1, 2, and 1, 3, so that's the Stanley-Reisner ideal. That's being tensored with some exterior algebra on U1, U2, U3 in degree 1. And d of ui is vi as usual. So you can just compute here, and you see that the only things that can be closed and not exact are in these degrees, like so corresponding to the missing face 1, 2, you have a class represented in the Kazul complex by V1, U2. Similarly with V1, U3. Right? Both of those are closed because d of v is 0, d of u2 is v2, but v1, v2 is 0. So same thing here. So here's a basis for cohomology. And then we can think of this exterior algebra module structure in this case. Iota 1 and iota 2 are only non-trivial like here and here. Maybe minus iota 3 would take this class to this one, and iota 2 should do that. Right, it's just differentiating away this u3 or the u2. And for degree reasons, that's the only place you could have a non-trivial derivation of degree -1. So that's the whole lambda module structure in this case. And what does this have to do with the minimal free resolution? Sorry, maybe I should also say in terms of this second bullet here, like you can see these maps in the Hoxter decomposition also, because there you just take like this full subcomplex on 1, 2 is corresponding, right? That's a copy of S0. So its generator H0 is corresponding to this class, right? And if you just included the full subcomplex 1, 2 into 1, 2, 3, well, that's just an equivalence, because this full subcomplex is also just a copy of S0. So that's giving you a non-trivial map right there. Same thing with the other one. Okay, so the point is that this information is telling you a good part of the minimal free resolution. So more generally, a torus action gives you a whole bunch of higher cohomology operations. The exterior algebra that I just described sits inside of a larger algebra of higher cohomology operations that's acting on the cohomology of any space with the torus action. So Gresky, Kotwitz, McPherson introduced these higher operations. They just have these odd degrees. They're of degree like 1 minus twice the degree of S, where S is just any monomial in your polynomial ring here. And in the case that their monomial S is just like a variable Vj, then that's exactly this derivation. So the secondary operations indexed by quadratic monomials would go down by degree 3, and so on. And if you included those ones into this picture, I won't say much about how they work, but they're higher operations that feel a lot like higher Massey products. And in this case, okay, I should now call this maybe delta 3 and delta 2. And then some higher operations down here corresponding to these missing faces of delta 1, 2 and delta 1, 3. And then the theorem is just saying that this picture is all the data of the minimal free resolution of this Stanley-Reisner ring. If you just take this picture and sort of turn it on its side and tensor with S, that's how commutative algebraists draw a minimal free resolution. And all these operations assemble into a differential. You just look at S tensor the cohomology of ZK, and you define a differential by just summing over all the square free monomials, multiply on the left by that monomial S when you apply the operation delta S on the right. For moment angle complexes, it turns out only the square free ones can be non-zero. So I can also write this like this, right? Think of a square free monomial as just a subset of our vertex set M. Okay, so like I said, the point here is just that the lambda module structure is exactly the data of like the linear component of a differential in a minimal free resolution. So to know the moment angle complex with this module structure is to know, all the modules, right? So the Tor algebra, the Stanley-Reisner ring, together with just the linear component of the differential. And then you could study these higher operations to get at the higher components of the differential. They won't be so relevant for this talk, except for the fact that in homological degree 1, so here, this is homological degree 0, this is all homological degree 1, and this is homological degree 2. Projective dimension is 2. You always have, in homological degree 1, your missing faces indexing some higher operations connecting your missing face classes to like H0. Yeah. Please, yeah.
Is this arising from the Taylor resolution?
It could. We just use the Kazul resolution, the Kazul complex, and apply the homological perturbation lemma, but you could take any resolution.
So do you understand yet how this Taylor resolution approach corresponds to taking the Kazul resolution and doing HH, the double homology? Is there a connection between those two lines of thought?
There is, yeah. HH, double homology, is just when you take the cohomology of the cohomology of the moment angle complex, right? I would maybe call this like sub D or something, or I don't know what the notation is, some differential of degree -1, and this would just be this, right? So for any torus action, you get some induced operation of degree -1. For double homology, it's just a very specific piece of the linear component of the. So yes, this information is completely contained in the linear part of the minimal free resolution. And higher operations don't come into double homology, but this operation right here would also induce higher operations, and knowing all of those higher operations is what you need to get to like the equivariant cohomology with respect to the diagonal circle action ZK. Okay, so there's some background on the minimal free resolution and a sort of topological interpretation of it I'm going to be using. So now back to this main problem of the homotopy type of ZK. So there's like a long history here of identifying when the moment angle complex could have the simplest possible homotopy type. Just a wedge of spheres is about the simplest thing it could look like. And I'm being a bit unfair here and condensing a lot of beautiful work into like one theorem, but I think basically this maybe started with a result of Grbić and Terrio, which gave a very specific wedge decomposition for the moment angle complex associated to just M disjoint vertices. And then they later generalized that to any shifted complex K. Also has the homotopy type of a wedge of spheres. Stephen went over the sort of inductive proof that can handle these two classes to show that ZK has to have the homotopy type of a wedge of spheres there. And then Velker and Grbić showed it for vertex decomposable spaces, showed much more. All of these results are slightly different and do different things. Some of them involve like desuspending the entire BBCG decomposition, so it's not just about the moment angle complex necessarily. And about the most general class we know, where the moment angle complex is a wedge of spheres, are these dual sequentially Cohen-Macaulay complexes. So if the Alexander dual of K is sequentially Cohen-Macaulay, then ZK has the homotopy type of a wedge of spheres. So these first 2 or 3 are some very like rigid combinatorial definitions I won't give you right now. And then it was realized that these all fit inside of this much bigger class of sequential Cohen-Macaulay complexes, or sequentially Cohen-Macaulay complexes more generally. And the definition there is a bit more loose and homological as opposed to combinatoric. But none of these proofs use the following classical results from commutative algebra. Egan and Reiner showed that K is dual Cohen-Macaulay if and only if its Stanley-Reisner ring has a linear resolution. And a linear resolution just means, okay, beyond the first differential, which is just the data of your missing faces, like I said, if the only entries in the matrices describing the differentials in your resolution are all just monomials, right? So the matrices describing these differentials have entries which are monomials in S, and if you only see linear terms there, then you say it's a linear resolution. So these are just linear syzygies. If that's all you see as you move along the resolution, then you say it's linear. And so you could, what I want to do is sort of rephrase some of these results using this theorem here and some variants of it. So I've just said dual Cohen-Macaulay as opposed to dual sequentially Cohen-Macaulay, but shortly after this, there's a variant that says if K is dual sequentially Cohen-Macaulay, then the Stanley-Reisner ring is component-wise linear, which means something very similar. And then there's a whole bunch of different versions of this theorem that came after that in commutative algebra. So I'll mention some of those in a moment, I think. But the way I want to first just rephrase this theorem maybe is just to show that everything in the linear strand of the resolution is always in the image of the Hurewicz map. So in this case, ZK is of course the only thing it could be really with this cohomology. It turns out to be S3, wedge S3, wedge S4. And about the only thing that's obviously in the image of the Hurewicz map for a moment angle complex are the minimal missing face classes, these classes corresponding to your missing faces of K. But beyond that, I just want to say that anything that's connected to this homological degree 1 stuff by primary operations or linear monomials in your resolution are also going to be in the Hurewicz image. So if you had a linear resolution, everything would be in the Hurewicz image. And that's one way to see why the theorem above is true for all of these classes of complexes. So I'm going to next phrase a theorem which is like a bit more than you need for those purposes that I just described. But here's a theorem that's true for lots of torus vibrations, but not all. So phrased in terms of moment angle complexes and this vibration right here, relating ZK to DJ. Start with just any homotopy class, pi n ZK, and also let mu I be like the inclusion of the bottom cell of the ith coordinate of CP infinity. DJK here always contains like a m-fold wedge of CP infinities, so you can include the bottom cell to the ith coordinate. And the theorem is like if h of f denotes the Hurewicz image of f, then acting on it by like the sweep action. So now I'm switching from cohomology to homology because I want to say something about the Hurewicz homomorphism, but exact same way, this torus action is giving you a lambda module structure. Calling my generators lambda now, so let's just remember they have degree +1 now instead of -1. So they're going up by degree 1 in that picture over there. So if you act on something in the Hurewicz image, h of f, then I want to say that's still the Hurewicz image of something. And there's really only one thing it could be if you think about this vibration here. So the mu I is also the bottom cell of BTM, or one of the bottom cells of this product of CP infinities over here. So it definitely doesn't lift to ZK. But if I compose F with omega, and then I take the Whitehead product of those two things in here, then that Whitehead product will have to map trivially to BTM since it's an Eilenberg-MacLane space. So you get a lift of that Whitehead product to ZK. And a lift is unique because this vibration splits after looping. So this bracket with a bar over it is the unique lift of that Whitehead product. And I claim the Hurewicz image of that is exactly the sweep out of this homology class, h of f. And
this omega is an ordinary Whitehead product or higher Whitehead product?
this
Is this
gonna be
omega
ordinary.
ordinary Whitehead product or higher Whitehead product?
Just the ordinary. We just have two maps,
And
SN into DJK and S2. I'm just going to consider their ordinary whitehead.
but is it also of those type of iterated whitehead product of those mu i's, or it can be whitehead product of something else?
It can be whatever, like F could be whatever you like. So you might be thinking of taking F to be the lift of a higher whitehead product of a bunch of other mu i's, right?
Okay.
You can iterate this. But I just want to consider not just the lifts of whitehead products, but just everything in the homotopy of ZK.
Okay. Okay. Thank
But
you.
yeah, you're right. You could start with F to be already something of this form, right?
Right.
Thank you.
Are there any other questions for Steve at this time? Anybody? Thanks.
Okay, so this is a place where some polyhedral products show up. So I wanted to maybe sketch some idea of the proof here. It's very... so starting with S n plus 1, there's just the universal whitehead product into here. So here's like iota n, iota 2, the whitehead product of the inclusion of these two things, whose cofiber is just the product of Sn and S2. And I want to think of this sphere as a polyhedral product in the usual way, namely as like the boundary of dn cross d2, right? So dn cross S1 union S n minus 1 cross d2. And there's a well-known interpretation of the whitehead product in terms of polyhedral products, where you just think of the sphere in this way, and then you just pinch the boundary of all disks to a point, right? So if I did, Q cross Q, where Q is that pinch map, and this becomes an S1, this becomes a point. So you're looking at Sn cross a point, union a point cross S1, and that's exactly the definition of the wedge. But I'll think of doing that piecewise. So first, imagine just pinching in the first coordinate. That would get you to here. Okay, so Sn minus 1 becomes a point cross D2. And then I can do the identity cross, pinch in the second coordinate. That gets you down to here. And then along here, I really want to look at this whitehead product of mu I and omega composed with F. Okay, I have Sn here, so I should write like this, I think. Let me just put the identity there for now. And up here, I could just do F cross the identity to get to ZK cross S1 union a point cross D2. And then what do I put here to make this commute? So let's just also pinching this disk to the sphere. Okay, and then lastly, I just need to fold these maps together. I do the universal whitehead product, and then I do my two maps on either side, F composed with omega and mu I. So here's just like the identity map and mu I folding into DJK. Here's omega. And here I have an action map, like consider now the ith coordinate action. It's a circle action on ZK. Might call that AI. And that action extends to this cofiber here, so the AI bar. So this last map is just the action of the ith coordinate. And then you just have that this whole bottom row here, the bottom composition, like Sn+1 to the Davisy-Niskevich space, is just the Whitehead product of mu I and omega composed with F. I can write it in this way since mu I has degree 2, this thing is commutative. And so my top row is some lift of omega, and lifts are unique, so this must be the unique lift. Okay. Yeah, this is the unique lift of the Whitehead product. Usually Whitehead products are of no use for studying the Hurevich image because Whitehead products always have trivial Hurevich image. Their suspension is trivial. But this lift of a Whitehead product might have a non-trivial Hurevich image, and you can check that in fact it does. So all of these spaces up here are polyhedral products associated to just two disjoint points. These two things are really just like half smash products. So you can just track very easily using polyhedral products or without to see what this map does in homology, to see that this Hurevich image is what we want, right?
Excuse me, Steve. I make a comment about this. In fact, Martin and I were discussing this map recently, and we both thought it would be very nice if you could prove that the top map is essential. Oh, I think it.
I was putting my hand up because after you're done, I wanted to ask a question to Steve.
Oh, so can I continue?
Yes, of course.
And we thought about it, and it would be very, very nice to have a purely combinatorial proof of the fact that that top map is essential. Well, that's my comment. Are there any other comments?
I just wanted to ask a question. So that's showing that something that is in the image of the differential is also in the image of Hurevich. Is that the point?
What differential?
Well, I mean,
like this
you have
lambda.
multiplication by AI. AI is like a differential for one of the actions of the sweep action.
Yes, I'm thinking of AI as some sort of ith coordinate circle action on ZK. Yes, so what this map does to a homology class or a cohomology class in ZK is the sweep action, what I'm denoting by this little lambda I action. So yeah, you can just see that this first map, so this is just a sphere of dimension n+1. It's easy to see that this half smash product is a wedge of spheres, like if I draw a picture imagining n to be 1. So let me start over here. Here's my one disk cross a circle. And then I'm just pinching the first coordinate, so this disk will become a circle. So that's now looking something like that, right? And this is clearly homotopy equivalent to Sn, in this case, S1 drawing. This case. And it's easy to see that this first map is just the inclusion of Sn+1 into the right summoned here. And then the second map, like I said, is really just like a half smash product. If you think of both of these unions as pushouts, or one of the corners is contractible, they're both just like the co-fiber of the inclusion, the intersection into one. So this map is just like F half smash the identity. So it's easy to see that it's like the image of the fundamental class here is going to go to the Hurevich image of F, tensor the fundamental class of a circle in here. The cohomology of this is really a tensor product because this is a half smash product. So it's just the tensor product of ZK and S1 with like the S1 generator removed at the bottom. But this product is still there. And then what this action map does is exactly sweep, right? So this is by definition like lambda I, as I'm calling it there, h of f. So that's how you can see, Tony, that this map is essential. And yeah, like you said, this diagram I think has shown up in other places, in a paper of Panov's and Abramyan's in particular, where they're thinking of F as maybe a higher Whitehead product. Consider a similar sort of argument like this. Okay, and the corollary is just that, okay, the Hurevich image is closed under the sweep action. We know that these missing face classes at the bottom in homological degree 1 are always in the Hurevich image. So everything attached to that by primary operations or by the linear pieces in the minimum free resolution is also in the Hurevich image. So this is called the linear strand. Everything connected to homological degree 1 by degree 1 stuff. That's all going to be in the Hurevich image. And then, fun fact, something is a wedge of spheres precisely when the Hurevich homomorphism is surjective, right? If you have every homology class being hit by some map from a sphere, you can just add all those maps together to get an equivalence like this. So the corollary that I sort of already described is just recovering the, I guess, dual Cohen-Macaulay case by Egan and Reiner. K is dual Cohen-Macaulay, if and only if this thing has a linear resolution. So this is just my rephrasing of that theorem of Irie and Kishimoto. And a bit more generally now, here's that analog of Egan and Reiner that says, okay, a Cohen-Macaulay complex is pure, so all of its facets are of the same dimension. And the dual of that is like saying it's Alexander dual, all of its missing faces are of the same size. So sequentially, Cohen-Macaulay is just some non-pure generalization of the Cohen-Macaulay property, which allows for a social complex to be not pure, or dually, your missing faces, or like the generators of your Stanley-Reisner ring, don't all have to be in the same dimension, like that example up there, right? You could have missing faces of different dimensions, but it still sort of makes sense to talk about a linear resolution or linear strands above any of those degrees. So using that corollary back here, that the linear strand is in the image of the Hurevich map, together with this other bit of classical commutative algebra, you get this other result. So again, this could be phrased, if K is dual essentially Cohen-Macaulay, or if it has a component-wise linear resolution. And then one other result I didn't mention on that previous slide, but a nice one that came up last week also, is if K is flagged with a chordal 1 skeleton, ZK is known to be a wedge of spheres. And you can also see that easily using this as well, because the classical result of Freiberg says that this is precisely the case when a quadratic monomial ideal has a linear resolution. Okay, I don't want to run out of time. So like I said, all of these results were already known. We're just sort of getting at them in a different way that doesn't involve having to dualize, thinking of the Alexander duals of simplicial complexes. And the initial motivation for all of this was to understand the homotopy types of moment-angle manifolds. So in terms of moment-angle manifolds, remember that's the moment-angle complexes associated to Gorenstein complexes, or like sphere triangulations in particular. About the only classes of Gorenstein complexes for which a moment-angle manifold has really been identified, like up to homeomorphism, are ones coming from work of Gittler and Lopez de Medrano, and a few others that identify the case. The moment-angle manifold is a connected sum of sphere products when your simplicial complex is like a stacked polytope. So something you can get from starting from a simplex and doing vertex cuts, or dual neighborly polytopes, or sphere triangulations that are neighborly in the sense that like a d-1 dimensional sphere triangulation, every d over 2, set of d over 2 cases are connected. Every set of less than or equal to d over 2, like half the dimension, vertices should span a face. Yeah. Okay, but they could never be a wedge of spheres, right? So you could never have like a fully linear resolution for a manifold. There's going to be some cut products, so that can't happen, but the point is you can have a linear resolution all the way up until like the very last attaching map, essentially. So a simplicial complex, especially if K is Gorenstein, is called almost linear if its resolution is linear for p minus 1 steps, where p is like the projective dimension or length of the entire resolution. So this is basically what's happening in all those examples where moment angle manifolds have been identified already as a connected sum of sphere products. So we wanted to try to see these in a more homotopy theoretic way because Gittler and Lopez de Medrano's results use like H-cobordism theorem, and they really use the smooth structure of a moment angle manifold, so they only apply to polytopes, like sphere triangulations that are polytopal. But there are tons and tons of sphere triangulations that are not polytopal and have similar homological behavior, so we just wanted to see if we could recover their results in some sort of simpler way. So all of these examples that I sort of just mentioned have an almost linear resolution. The boundary complexes of polygons. I'll show an example of that one at the end, I think. These all have resolutions that sort of look like this. If K is an M-gon, the boundary of an M-gon, then you'll have a bunch of missing edges. Those are the only missing faces. They'll all be connected to the bottom class in H0 by some secondary operations. And then above that, you only have primary operations. So you have like a sequence things, then you have a top class somewhere. And you'll have some secondary operations by Poincare duality, which are just like the mirrors of what's going on down here. So you just have a bunch of like primary cohomology operations, and then this and this of secondary. So that would be like the classical example of an almost linear resolution. You have above homological degree 1, it's all linear terms, except for the very last step. And then you might ask if there are any others that look like this, and polygons fit into a wider class of polytopes called cyclic polytopes, and they're the ones that would have, instead of degree type like 2, 1, 1, 1, 1, 1, 2 like this, it'd be maybe 3, 1, 1, 1, 1, 3, or 4, 1, 1, 1, 1, 3. So those are strictly almost linear resolutions. And by the upper bound theorem, any simplicial sphere, which is neighborly in this sense right here, has this like extremal property that they simultaneously maximize the face numbers of the simplicial complex. So you might think that they're, because they have this extremal behavior, neighborly complexes, like all of these examples are neighborly, they might be very special. You might think that they're very rare, but it turns out that there are lots and lots of them. They grow super exponentially in the number of variables, and there's a lot of conjectures by combinatorics here, I could say, about families of neighborly simplicial spheres that are non-polytopal that have been constructed. But to give the impression that there are lots of them, I just wanted to give this conjecture of Kalai, which sort of suggests that they might even be sort of generic among sphere triangulations. He suggests that the number of neighborly n-1 spheres on m vertices, oh, there should be a log here, pardon me. This is definitely not true. I meant to have the limit as m goes to infinity of log of this number over log of that number. That's perhaps 1. I think it's considered a very bold conjecture in combinatorics. They're nowhere near proving this, but there are very good like asymptotic results about the numbers of these things as the dimension or the number of vertices grow. So the point is there are just lots and lots of them that are not coming from polytopes. And then same thing, if your missing faces aren't all in the same degree like this, you can talk about sequential Cohen-Macauliness or component-wise linearity. So now call a simplicial complex component-wise almost linear. If, well, okay, the easier way to say it, this isn't the usual way to define it, but it's the same as saying that the linear part of the minimal free resolution is acyclic in the middle. So if you think of the way I described the minimal free resolution earlier, as just like S polynomial ring tensor to the cohomology of our moment angle complex, some differential. Then in the middle of your resolution, or in the middle cohomology group, if you had some class alpha that was in the kernel of all the like primary operations, all the derivations of degree -1, then that would give you something that's, you know, not acyclic, right? Because you could consider just like one tensor this and the linear part of the, so that's definitely not in the image of any differential, because D multiplies on the left, like the maximal ideal. It increases the dimension on the left side of the tensor product, in other words. So this would certainly be not exact in there, but it would be closed if alpha did not support like a primary operation. So to say the linear part of the minimal free resolution is like acyclic like this, it's just to say everything in the middle has a primary operation coming out of it. Dually in homology, any homology class that isn't like the top class or one of these homological degree 1 pieces can be reached by sweeping out some of these bottom classes. Or in terms of Hochster, this is just like take your missing face classes and think of those bottom pieces of the Hochster formula, and then just include full subcomplexes into bigger full subcomplexes and see how these classes persist. For lots of polytopes, that just exhausts the entire cohomology of ZK. Okay, so I think this was just the last thing here, right? The point is, K is a sphere triangulation, or more generally, any Gorenstein complex, and it has this component-wise almost linear property, then that's saying a lot about its homotopy type. So it's like n-1 skeleton would be a wedge of spheres, right? Because everything is in the image of the Hurevich map except for that top class, which must not be a Hurevich image because it's like a product of things by Poincare duality. So that's enough to conclude that ZK is at least rationally a connected sum of sphere products. So all of these moment angle manifolds are formal. They're rationally looking like connected sums of spheres. And integrally, their loop space is a product of loops on spheres. I think later this week, we'll hear more about this problem from Lewis, about when can the moment angle complex be decomposed like this in terms of familiar spaces. So this is a good example where that happens. Again, this is sort of the simplest homotopy type the loops on ZK could possibly have. Okay, so the examples here I didn't mention, but you know, these component-wise almost linear ones include all of these, of course. They also include stacked polytopes. So if you take a simplex and start doing vertex cuts, you won't have all your missing faces of the same dimension, but it will still have a sort of component-wise almost linear resolution. And we showed that if you take any two component-wise almost linear sphere triangulations and consider their connected sum, you get another one. So in particular, that means you can take a connected sum with a simplex. That's what corresponds to like vertex cutting. So you take any of these examples we've discussed so far and start doing like stellar subdivision in any way, you'll stay inside of this class. And you can, you know, take connected sums of like cyclic polytopes and stacked polytopes, things like that, to get tons and tons of examples. Okay, I guess this is just a better drawing of like what I had here, right? In the case of a pentagon, you can consider all of your missing face classes, like vertex 1, 3 is a missing edge, vertex 1, 4 is a missing edge, and so on. So they'll be connected to homological degree 0 by these secondary operations. And then if you just consider like the missing edge 1, 4, that's just a copy of S0, right? If I include it in vertex 5, then I get something contractible. So that map is null homotopic, so this shouldn't have like a delta 5 connected to it. But if you consider 1, 4 and include it into the full subcomplex 1, 2, 4 or 1, 3, 4, those will be equivalences. They're inducing non-trivial maps. Those are giving you some like primary operations like this. So yeah, usually you can't do this, of course, like take an element in the nth homology group of some space and like just push it up to the n plus first one. But if you have a Hochster sort of formula for your cohomology, you can do this. And also if you have a circle action, you can do this. You can sweep out an n-dimensional homology class to get an n plus 1 dimensional one. And for moment angle complexes, these two things coincide as you just take these bottom classes and push them up into higher degrees, you stay in the Uravid change. Okay, I'll not give another example, so thank you very much.